Good afternoon, everyone, and welcome to yet another seminar series. Today is December 17. We had a chance to host Professor Aniruddha Mitra here from all the way to the United States. Let me just do the brief introduction. And he got his Bachelor of Science back in India in famous IITs, and he completed his PhD program, University of Nevada, in United States. If I recall correctly, it was 95, right? 1995. From then on, he jumped on many different journeys in his career. But here today, he's going to present us his works as a mechanical engineering professor, and we will have a chance to listen from the very source of these studies. Without further ado, floor is yours, Professor Mitra.
Thank you very much. First, before I start. Everybody can hear, right? I don't need a mic, right? Okay. I would like to thank first Dr. Engin. He was my contact, and thank you for giving me such an opportunity to give a speech here in world-renowned university. Everybody knows about this place, and I'm honored to be here, give a presentations, which I never dreamed that I would do that in my life. So, with my research caliber, so to say. Now, just a little bit of background, as he mentioned. So, I have been in many different places with me, wearing many different hats, so to say, in terms of English proverb. So, basically, in our field, you go with the flow wherever it takes you, where the money flows, where the research field opens up. You do not dig into the same thing again and again, unless and otherwise you have your own big resources. So I'm one of the persons who started my career as a composite, very traditional mechanics person who would be going through the composites, matrix composites and things like that, equations of Hooke's law, extended Hooke's law, and these kind of things. But I did that some, then went to the vibration a little bit. Then guess what? I am slowly dragged into the field that nobody will think that mechanical engineering will be associated with that. It's all about these guys, masks. See, this one and this one. So let me tell you what the starting point was. Some of you guys are well-renowned faculty, some of you guys are students. Let me tell you a good story about the mechanical engineering student, and that comes from me. We can fit anywhere, any discipline, any type of thing. They need us, whether it's bioscience, whether it's some kind of a health science issues. We are there to help. We can fit anywhere in the world, any discipline, to be honest with you. That's what are my personal observations. Now, how did it start? And I was talking very briefly. We were trying to do some analysis using the construction sites, how these masks are good, And there was two persons. I was facilitating a meeting. The meeting was taking place between a civil engineer, is a construction guy, and another person was health science guy. So they were thinking to write a grant, an NIH grant, and they decided to write the grant, but they felt very bad that the meeting was taking place in my room and I'm out, being a mechanical. They looked at me and I said, okay, I will do the instrumentations and data analysis. How is that? So they put a grant and the grant was funded. Rest is history. So the money came there and my lab developed. It is Krypton 85, those kind of isotopes are sitting in my lab instead of a chemistry department. And it's basically biohazard lab, so to say. The only biohazard lab in the entire university, where I have to pay $1,000, $2,000 per year just to keep those instruments as their license, things like that. So in this particular study, actually, I am very much my co-author and co-researcher, I would say. He is an assistant professor. Mostly it is his idea. I am just going to put the things together and let's see how it works out. So that's what it is. So what I'm going to say is introduction, a little bit of background, experimental methods, results, discussions, experimental uncertainty, conclusion, acknowledgement, reference. I must admit there are a lot of answers I do not know. You might ask me and I will give it a try, but I don't know the answer because I have published quite a few papers on these kind of subjects, but all the papers, the introductions are written by the persons who know more knowledgeable, bioscience guys, environmental science guys. I just write down the results, instrumentation, these kind of things on the paper. So this is what I'm going to talk about. The filtering faceplate respirator, which you called mask. This is not mask is not a very good health science term. That's what it is. Filtering facepiece respirator, FFR, N95. That means it's supposed to filter 95% of the particulate. And surgical masks, this is surgical mask, are widely used to protect individual from their environment and the vice versa. Okay, that's what it was. During the COVID, before that, well, you really do not see much study on these ones. During the COVID, we started to think about it quite a bit. First of all, if you remember correctly, the masks were scared. You do not find the mask. They were short supplies. You have to wear the same mask again and again, 5-6 times. Reuse them. Using the post-COVID area, people use these face pieces, especially FFR N95, quite extensively. Multiple, instead of single use, has been very common, so as prolonged wear time. So you have been putting there for 2 hours, 3 hours sometimes, that's very normal, or maybe an hour, that's easily. We got used to it. Nowadays, if I put the mask on, then I will feel very uncomfortable. But those days, think about it, if you are out, you automatically make sure that your masks are on, right? That's what the days were. So the question is, well, it is one-time mask usage and throw it out. N95 works very good. It's no problem there. But if you keep on using it for extensive hours with different operations, for an example, if you are just laying down with, say, let us say 17 liter per minute, that the standard breathing, relaxing, versus a mediocre walking down like this, 30 liter per minute, or 45 if you run, how this mask performs. And we are talking about not half an hour, not 2 hours, not 4 hours, not 8 hours. How these guys are good about that one. So that was, we were trying to figure out, so to say. And again, as I said, the data are all over the place sometimes. You have to really sit down and look the data different ways, different types. Find the percentage leakage for light and moderate intensity of breathing. We did not have the perfect tool for higher breathing rate at that time, 45. We did not conduct that, but at least on this particular study. Find the percentage leakage for various levels of wear. Find the percentage leakage under short-term and long prolonged wear time. Compare the rates for N95 and surgical masks. So there are quite a few of parameters. If you can look at that one, I'm just going to go next slide. I can show you the filter type. One is N95, one is surgical mask. Mask usage, 8 hour used, 4 hour used, and completely unused. So 3 types. Somebody wear 8 hours the mask, somebody wear 4 hours the mask, and somebody didn't use the mask at all. So there are 3 types. There are 2 types of mask itself, surgical and N95, this type. Okay. And then we run the experiment with 2 different flow rate, 17 liter per minute and 30 liter per minute, 2 of them. So, and then we dragged the experiments, run that experiment for 30 minutes, then used another one 2 hours, then another one 4 hours, then another one 8 hours, continuously running it. So if you do the combination there are 48 different type of combinations. You understand that one? So mass type, flow rate type, how much it is used, and how much it has been going through the experiment. If you consider those 2 times 3 times 4, 48. So we have 48 different data for different for each combinations. And we did more experiments, but 48 to the basic ones. So this was the, I'm going to say it is a very rudimentary, elementary sketch of the flow, how it is happening. This is the pump which you can change the flow rate 17, 30, 45 if you want to. This one. This is at the middle yellow one is the 3-way valve, and this is the particulate chamber, and you see there is an HEPA filter. HEPA filter, you know that one, it's in the plane. I noticed that when I was getting into the plane, HEPA filter is there so that the air comes purified. So HEPA filter. So this one is always negative because the pump runs and drags the air from the particulate generate chamber, and then it will push to the mannequin testing chamber, the one at the top. Okay. So this is the basic structures. This is the basic way we have done the experiments. Okay. So if I'm going to go back and forth, the particle generating chamber, mannequin testing chamber, and the pump and 3-way valve HEPA, you can find many of them here. As you can see, the first top one is the basic combination of 3. The left side is the pump, right side is the particle generating chamber. The top one is the mannequin chamber. We measure by TSI side pack the PM 2.5. You guys know that one. The particulate up to the 2.5 micro diameter per meter cube. It is in microgram per meter cube. And this is the mannequin. This is the vacuum breathing simulator. TSI porta count. We use the porta count to make sure the fit test on the mask. TSI particle generator. That basically generates salt, to be honest with you. You have a standard liquid there, standard water, and you put a salt tablet there and turn it on, it will keep on generating salt. So the salt is passing through, as you can see, from the 3-way valve and going to the mannequin chamber by the use of this pump. So that's what the experiment is. Then we are measuring the data using 3 sensors from the particle generating chamber and 3 sensors from the mannequin chambers. This one and that one, these 2. Okay. The experimental procedure was purge chambers with HEPA filter air, stop pumps and filtered air, fill and turn out the TSI aerosol generator, run the aerosol generator until the concentration reaches about this much, place mask on the mannequin, complete the fizz test using the TSI porta count, start breathing simulator, which is the pump, and TSI side pack center, run the breathing simulator for desired time span, which is half an hour, 2 hour, 4 hour, and 8 hours. Okay. Data analysis overall. The data was collected every 10-second interval, 30 data points for 5 minutes. About 30 data points for 5 minutes, and I will tell you why it is that important for 30. The data is collected via 3 sensors from each chamber and averaged. The data represents PM 2.5 particles that are 2.5 microns or less in diameter, measured in microgram per meter cube. Then this one That was the contribution from the guy from health science department. So what he did, let us say, for 5 minutes you collect 30 data. That means for an hour you collect 30 times 12, 360. So for 8 hours is 2,880 data. Then what he did, for each concentration, he took the average. All those about 3,000 data this side and 3,000 data this side, and find out the leakage rate, so to say, outward leakage rate. Okay, you are coming from here, outward leakage rate, how much outward leakage is happening. And I, as a mechanical engineer, I said, how in the world you expect that to be steady? Your particle generation rate changes, correct? And your rate may be changing abruptly at some point of time. How do you know it is not random? It could be, the data could be all over the place. How do you know that one? Because you are measuring 8 hours and then take the average right from the beginning to the end. So I said, okay, I'm not very satisfied with your results here. Let's do this. So I jumped in. I said, okay, let's do this. We will do, so to say, the rate at certain points. Let us say at the beginning, after 30 minutes mark, after 60 minutes mark, after let us say 90 minutes mark, 120 minutes. How did I do that? I said, the 30 numbers is based on the Gaussian data, it's satisfactory. So I said, why don't you take 5 minutes of data at that instant? 5 minutes of data from the other side, other column at that instant, and find out the average. See whether that kinds of fits your overall line. You see the point what I'm saying? So your data does not change, your filtration level does not randomly changes all over the place for 8 hours. I just wanted to make sure. OSHA said it should be very standard, but I did not believe myself to start with, as I said, as a mechanical engineer. To monitor the consistency throughout the prolonged experiment at a certain time stamp, 5 minutes of data from both channels are collected and analyzed. For a typical 30 minutes test, this is done twice, at the beginning and at the end of the test, by collecting first 5 minutes and the last 5 minutes of test. So for a 30 minutes test, you can collect first 5 minutes and the last 5 minutes. Just like that you guys do numerical differentiations, something like that concept, same concept. That's what it is. And then for 2, 4 and 8 hours test, data is collected several times with maximum gap of 30 minutes. So of 30 minutes, another, yes, then you cover for 5 minutes, and then you do not take the data. Another 5 minutes, we collect the data and analyze it. For the analysis purpose, data is already there, huge data amount. Okay, now see, this is the mannequin chamber, and this is the particle. So particle generated chamber is at the beginning is very high, of course, because it is generated. Then it is getting pumped into the mannequin chamber, and data are, you see, going back and forth a little bit. This one is more of a steady, but that one is, and this one for 2 hours data. Did you see that one? How consistent they are? So the blue line at the top is the overall average, and the dots are individual data points. At that point, what was the filtration level? They pretty much match. I was so impressed. I told him that your theory is correct actually. It does not jump back and forth. Even though the generation can be jumping back and forth. You can see that one, particle generation and mannequin chamber, but still it is sort of holding true. Of course, for 30 minutes, it's a good idea to take the average, because the first one was very low, the second one was very high, because it did not stabilize at that point. Later on, looking at the data, we should have been, when we are going to, actually we are publishing a paper, we will say we'll cut off the first 20 minutes of the data. It's not useful. You see that one, it's still not developed yet in both those cases. Did you see that one? So that was, while analyzing the data, I could figure that out. This was for unused mask, N95, 17 liter per minute. This is unused mark, a 70 liter per minute. This one was for 8 hours data. Did you see that one? 8 hours data, but still the first data is so low. Then it becomes a little, did you see that one? After 4 hours, the things getting a little bad. Did you notice that one? Here, it is a 4-hour data. It has a tendency to go past. Initially, it was very good, but it has a tendency to overshoot the average at some point. This is the N95. The last two ones were N95 data. This one N95 and this one N95 for different times. Let's look at the surgical mask. Wow. So, surgical mask, this was 30 minutes data all over the place, already 50% over. This one is 2 hours data. This is above 40 as you can see, but it starts with about 25%. But this is the actual data from the particle chambers. These are in PM2, PM2.5, sorry. This one unused mask for surgical, the same type of data, and it is 8, you can see 8 hours. They clustered around a little bit higher after 4 hour mark, but 4 hour it is pretty good. Till the last point I did not like the last point. This point I did not like, but other than that it's okay. Here you can see it's deviate from the average quite a bit, but none of them are statistically significant. But this one was a surgical mask for 17 liter per minute. This one was surgical mask for 30 liter per minute. Look at the data. That one was about 88% average. Did you see the 88% leakage? This one is above 70% leakage. This is 30 liter per minute. So, with that, we going to go and show you all the 48 data points. These are the 48 data points. If you can see, unused N95 mask, 17 liter, this is 30 minutes, 2 hours, 4 hours, 8 hours. You can clearly see the trend. Did you see that one? That's going up. Percentage leakage is going up, outward leakage. This one is kind of an anomaly. 4 hour, 8 hour, 95, 17 unused, 4 hour used. It's already 4 hour used. This is 8 hour used mask. Okay, 2, 4, 8 hours. This is actually after 8 hours the ports gets clogged. So that's why the data are kind of an anomaly. There are some anomalies. This is 30 liter per minute unused N95. This is 4 hour used N95 mask, 30 liter per minute. This is 8 hour N95 mask, 30 liter per minute, and you can see the data in the bar chart. This is another one. So, this is on surgical mask, all of them, the similar data. You can see the clear trend here for surgical mask. It is clear trend that it is going up over the hours, the percentage leakage very clearly. This is 8 hour surgical mask. This one is 30 liter per minute. This is 17 liter per minute. This is 4 hour used mask. This is 4 hour used mask, 70 liter per minute. All of them are surgical. So, higher percentage leakage. You can clearly see that one. All of them are above 40, 45, 50%, this ones. Though all the data are very good, reasonable I would say, but all jumbled up. Let's take a look at better look. Let's take a better look here. Here we have combined both the type of N95 and surgical mask, not a very clear indications what is happening. Only thing, for 30 liter per minute higher the flow rate, you can see a slightly higher percentage leakage. This one is combination, if it is the hourly use, new lower side mostly 8 hours and 4 hours. 8 hours has some points that are here, as you can see, it's expected that. But it is a combination of both N95 and surgical mask. So we said that, okay, we now have to divide that and see one individually. Otherwise, this data does not reveal much. So we started looking just the N95, these ones. This one new, as you can see, it is quite below 20. This one, 8-hour used N95 is high enough. Some of them are 30-35%. This is 4-hour used. So this is supposed to be very good, and it is brand new. This one is 8-hour use. They are showing some wearing out. And this one is 4-hour use. It's somewhere in the middle, which confirms our idea. Then same N95, we have higher breathing rate. We have here higher percentage leakage, and this one is lower breathing rate, and this one has lower percentage leakage, as you can see. This one's okay. Now let us take a look at the surgical mask. The duration is exactly, so this is experiment is for 30 minutes, it's good. Then if you take 2 hours, data are showing some higher values. 4 hours, it's still higher values. For 8 hours, you see the data. So the surgical mask has a tendency to leak higher as we go on do the experiments. It's clearly trend. Unless otherwise you separate between two masks, it will not show that. Here, between the flow rates, as you can see, at 17 it is lower, at 30 it is higher. Surgical mask is quite higher that way. Okay. So this is the final point I was going to show you, because if this is basically between the surgical mask and this guy. Surgical mask, if you divide them and take all the data, this performance is way better. Actually 33% is the highest leakage we found with this one, versus surgical mask it went all the way to 88% sometimes, this ones. So with this analysis, this particular diagram exposes very clearly the effectiveness of this versus this. Okay, discussion. You can sit down and do lot of analysis out of it. I haven't done all of them, just here and there I was traveling and look at some of the data, and you can make a lot of information out of it. It's a huge amount of data. The highest leakage rate seen for N95 was 33%, and surgical is 88%. Outward leakage peak between 4 to 8 hours. So that was the main point of the results. We found out a lot of errors in our experiment. Some of them are minor, significant, can be tackled kind of things, and I as an engineer will talk about that one. I do not mind discussing them. First thing first, which we did not know, we presented this work in a OSHA's meeting, and we said that 8 hours they are wearing the mask. So of course it's not possible, right? So a lot of people open it, they timed it. That's what the students did. My students, honor students, did. They wear it, open it, wear it, open it, and still the total gets 8 hours. But they said that once you do 6 times, you are actually wearing this part. You are structurally no good. So after 6, this is not good. So only you can wear it, recycle it 6 times, wearing it and back and forth. That's what they said. I'm an engineer, so I just listened to them. That's what they said. So 8-hour test, I doubt anybody wear it within maybe 10 times. I do not know. So that's a part of the error. I have to admit that. Number 2 error, there is a drop in concentrations between the two chambers. We did it because we have to put lot of sensors, and that was very difficult to put lot of sensors, 3 sensors in the mouse. So we used 2 chambers, and as you can see, it takes a while to get into that equilibrium, so to say, the standard one. So we lost some data. Without mask, it was 95%. So it was pretty good data, as I can see. Pretty good, 95% leakage rate without the mask. So, so we can multiply with 0.95 or something like that, but that is okay. So drop in concentration in particle generating chamber to inside the ISO mannequin chamber. Mask held statically could not be readjusted. So once we start the test, once we put that in the fit test and start the test on the mannequin, it will go for 8 hours. If something happens with the fitness, and we cannot go back and change it, it has to be, just leave it like that. You see that? So it's an 8-hour test is quite time consuming, and students sometimes couldn't see that one. Sometimes they ran it over the night and make it run it. So that was one of the error. Sometimes we could feel that the particle is basically salt, NaCl. It's a standard tablet, they use it, standard water, standard temperature. That's how the TSI particle generator is there. So we found out between the 3 valves, sometimes it is actually gathering some. Once in a while, after 5 or 6 experiments, we have to clean up a little bit. So it was, we lost some particles there, obviously, that happens. So these are the sources of error. Now we are correcting those by checking with other instruments at this point as we speak. They are doing it, the experiments. Optical particle measurement, OPR N3, they are using it, much cheaper than these guys, these instruments guys, and we are using that to check our data. Conclusion. A mannequin-based simulation chamber was established for mask outward leakage test. It's an outward leakage, guys. Remember that one. Just in case, this is the outward leakage. You understand that this one is resistance to liquid. And initially, when I didn't know you can vary it this wide, this one is basically the liquid resistance, this part. And the white part is the absorbent. But it depends upon what you want. You see that? Sometimes you want to protect yourself from the environment, sometimes the other way around, right? You want to make sure your cough does not affect the environment. So that's a very interesting thing as such. Lowest outward leakage, whereas the surgical masks were more affected by usage durations. Okay. So I have some, mostly I as a professor go around with my hand waves and stuff like that, but actually the student does the work. So a lot of people knows that one, and I do not deny that. The students has to give them the credit. They do a lot of work. I sometimes do not rely them on the data analysis. I sit down and do that, but they did a fantastic job, especially the 8 hours and things like that. That's a lot of work they have done. This is one of them is the professor. He is from the environmental science, Professor Adhikari. He gave them some guidance, but the rest of them, Matthew Parker, Tanner Cohn, all of them got jobs actually. Some of them in nuclear power plant and things like that. So they got a lot of particle related jobs actually, one of them. One of them actually got into Tesla, and his work was particle counting or something of that nature. She didn't wanted to say it very clearly what it is for the privacy reason, but that's what it is. These are the references, and we have plenty of them. They're just basic ones I wanted to show you. And with that, I think, did the time was good?
Yeah, pretty good.
Yeah, do you want me to talk? I can keep on talking because I am a lecturer after the end of the day, but I thought I will just keep it. And
normally we do it like, maybe 45 minutes of presentation, last 15 minutes for Q&A, but it's already approaching 40 minutes, so it's up to you. If you have any other remarks, go ahead and add, or just like, go ahead and start Q&A session.
The couple of things we noticed here, not the science, the guys who are in the health science and things like that, health science, environmental sciences, they do not have a good coordinations with the engineers. Not good. That's what my general observation is. So you as a general mechanical engineer, as an engineer, can go ahead and ask a lot of questions, and I did. They were annoyed sometimes that this is not good, that is not good, this is not good. They go for a lot of overall averages, overall aspects, what is going on kind of things in an overall perspective. We as an engineer always try to think, hey, there is a small leakage there, why do you do not do that one, and etc., etc. For an example, I wanted to create a valve here. I just wanted to show you here, inward valve. I just wanted to show this one. One more thing. Right here, the particle generation chamber and the mannequin testing chamber. The particle generation is coming from, and the mannequin generation chamber, you are creating a positive pressure there. Did you see that one? That is positive pressure. This one is negative pressure. From the HEPA filter, it coming into that air. Yeah. So this is a positive pressure. So I was a lot of questions. Why there is a positive pressure? There must be some leaking. Did you hear the hiss sound, etc., etc. At the end, what we did, actually, that was my decisions to put a valve there. So outward valve, it will just go out, not come in the air. That's what I implemented there on that chamber, right? That chamber. So you have a lot of questions like that. When you are an engineer interacting with the health science guys, those are the things that you will see. I said, okay, this is too much of a pressure. How do you know it is? No, it is not that bad, but they believe on a lot of statistical averages and things like that. Not like us, I want the result right now, this is not good, that kind of thing. So that's what I would say our observation was. Basically, we did an extensive survey with these guys in our last research, which turned out to be good paper and stuff like that, regarding the how much leakage and things like that, hours and stuff like that. But this was more of an extensive use in the COVID era, how to use in over and over usage and things like that. That's what it is. Yeah, that's all I had to say actually. It's because, again, as I said, because of my ignorance on the subject, so I cannot speak more than that. So, but I will be happy to try to answer any questions you guys might have.
Thank you.
The floor is open for any questions if you guys want it. I have myself a question, but I just wanted to give you the first question right to audience.
I have two questions. First of all, you generate some particles. What kind of particles are you producing or generating for the test bench?
It is basically salt, sodium chloride. In the water, basically a sodium chloride droplets, if you can call it that way.
So how do you collect them in the test room?
Oh, it is generating.
You generate, but then collect to measure the efficiency.
Oh, this is what it is. I'm going to go you back there. Yeah. Yes, that one. Yes. Yeah. So this is the generating chamber, and then this one and going there, measuring there, right there. But
what do you measure in the test chamber?
Testing chamber.
Yes.
That is, we have three sensors there. We measure basically PM 2.5.
Yeah. Particles.
So particles.
Sure.
PM 2.5, which is, you know that one, the particle that have diameters 2.5 microns or less. until 10 nano with the instrument called side pack. We have 3 sensors there and 3 different zones. One is somewhere there, one is somewhere there, and one is somewhere there. Take the average of 3 of them in that way. And then, of course, that's what the measurement was, particle measurements. And then, as I said, we created the valve so that it goes out. Yes, some of the sodium chloride is outside, I'm guessing.
Thank you. My second question is about your flow rates you choose.
Yes.
What makes so special 17 liter per minute?
Very good question. This one, I asked the same thing when they started. 17, sometimes, if you see, sorry to say, this one, this is 17.
When I at rest.
Exactly. This is 30.
Walking.
I'm talking and things like that, 30. That's the standard they talk about.
I see.
17. And then there is one more, which we did not do that because of the flow rate meter we did not got that one. That was if you go and run, which I cannot outside, it's a hilly region. So that's 45. So it is very relaxing mode versus moderately active mode versus highly active mode. There are 3 zones, 17, 30 and 45. That's how they chosen. Because
so it is more than a prime number.
Yes.
Thank you.
Yeah, they fixed that. I guess that comes from NIH, National Health Institute. They designated this type of activities will cause this much of breathing rate, so to say. I'm guessing they have collected a lot of data from the human being who are running and things like that. And based on that, they found that average or something of that nature. I'm guessing, but that's those things standards for. It's not arbitrary as such. Otherwise, I could have been choked as my co-researcher's caller and say, hey, why did you choose that one? I have to answer Dr. Engin here. Go ahead.
Follow-up question on this matter.
Yeah.
Normally for humans, we just breathe in and breathe out. That's kind of sinusoidal wave.
Yeah.
How does this pump work? It's just continuous pumping.
Push.
It's just
Just push. Thank you. The breathing machine you can buy, that is about $15,000. The one which is go back and forth. This one just one way, as unfortunately. But as I said, you can. But we did not get that funded. We wrote the fund for that one where you can, and then so it has to be both ways, But that was way too expensive. It was not even the instruments. We borrowed some of them. It was for 2 weeks. It costed us 3 weeks $10,000 for 1 or 2 instruments just to borrow that one. So it was. Because the particle, I understand if the particle is bigger, you can measure it easily. If it is particle less than the micro level, then it is a trouble and you have to spend especially the nano range, it is quite expensive. So those instruments only a few companies make that. TSI is one of them. Even then they are quite expensive, but breathing machine, we couldn't afford it. By this time it is 20,000. We wrote the grant 5 years back, so I'm sure.
And one more follow-up with the surgical mask. You said if you want to protect yourself from environment, wear on one side, the other way wear other side. Could you just elaborate on that slowly so that we can speak?
The thing is that I was thinking, you see, this part is basically liquid repellent. You know that one, right? This side, you can Google it and find out. I mean, I'm not anything telling it very high as a very expert. I just know it. And this side is liquid repellent. You can see that one. If you spray liquid, you can go and spray liquid. It will not percolate to the other side. And this side is the absorbent, basically. So either way, I mean, you can wear it this way and you can cough here. This one will all work as an absorbent. So basically, you always wear, I'm not going to wear somebody else's mask, but this is why you should be wearing this way, always. And I told you that people think that, well, this way or that way, but this is what it is. This side is absorbent and this side is liquid repellent on this surgical mask. But they are not good for preventing as good as this guy. The trouble with these guys, as I said, is the fit test, because not every mask will fit you, fit me, or fit her, or fit anybody. You see the point? That's why we had to do a so-called quote-unquote fit test at the very beginning of the experiment, so that mannequin does wear it and have a pass the fit test. That means, that is why you see the hole here. We have one probe here, one probe outside. Make sure they are about the same, that it does not pass through. So we have to do the fit test using one of the instruments. This one's, I guess, TSI port account, which we borrowed again from the NSA.
Is a guy who worked on the powder-based method additive manufacturing in my PhD. We been regularly check with our mask. We were wearing P100 mask. It's just the big one that firefighters are using. So I know very well that it has to fit your face. Otherwise, if there is a leakage, there's no point.
No point. Yes, that's correct. That's right.
Gotcha. Any other questions from the audiences? We have Malik here.
Hello, sir. Welcome to Istanbul Technical
Thank
University.
You very much.
I have a question about page 16 and 17 at your graphs, at your tables.
16?
Yeah, first one is at 16 and the second one is 17.
Yes,
so,
yes, go ahead.
There is a separation between N95 and the surgery masks, and I was wondering what makes it very different from each other, that 8-hour timeline at the graphs. You see at the left side, top left side, you can see the 8-hour leakage is the highest rate.
Correct.
But the 4-hour used mask, the 8 hours test result is getting lower and lower. So what is the main reasons behind it? Because I was thinking about there is a particles stacked inside of the masks at N95. That's what I was just thinking about. Maybe I missed some points while you were talking to us, but I was wondering what is the main difference over here.
Okay, so basically you are talking about the 8 hours over there unused mask, but 4 hours used mask has a less one, right?
Yep.
That's right. So this is what the explanation I was given. Let us say if you have the particles, if you put it in the mask, after 2-3 hours, what happens? All the pores are clogged with the particles itself. So after, that's what I was saying, that after 4 hours, the things can be a little bit of confusion, because you might as well some of the pores leaked already. From some of the pores had been covered by the particles. That we found out in our previous experiments too, that sometimes it is, some of the pores are covered already. That's what we figured it out. So because we did some test, but that was not very conclusive once. We scrapped some materials and things like that. You did some test in lab, but it was not very conclusive as such. We found some particles on these ones, but whether that affects never know. And this is somewhat, as I said, this was somewhat statistical. You never know what is happening actually. One of the things, I mean, we have to keep on doing that experiments with 3, 4 different 6 times, and doing the 4 hours experiment, it takes a lot of time. That's what it is.
I got a follow-up question about it. You made this test with the sodium chloride particles, right?
That's right.
So sodium chloride particles are big enough to stack into these masks, but I was wondering why you choose sodium chloride especially, because in our breaths, I don't think that we don't breathe out sodium chloride. So sodium chloride is kind of big particles. So it made the stacks, it might be stacked on the masks. I'm talking about N95. But when we go past to surgery masks at page 17, so when you see the 8-hour test results, yeah, the results are getting bigger and bigger. So I was wondering, what if we use how can I say?
Smaller particles.
Yeah, smaller particles. Yeah,
Yes.
thank you. Yeah, you were only used with sodium chloride particles.
That's correct.
But in our breaths, we are not breathing out sodium chloride, but we are breathing out oxygen, for example, carbon dioxide, carbon monoxide, etc., etc. And these particles are smaller parts. This is my opinion. So why did you choose sodium chloride in your test?
Okay, this is good. Very good observation and very good questions. To be honest with you, I don't know the answer. Because that's what the health science folks standardly use that one.
This is some kind of standard then?
Yes, that is a
okay.
standard from the OSA. So when you buy this, so to say, it's a very good question. I mean, and I did have some kind of a concern on that one. First of all, it has to be, all the test has to be standard. You see the particle generation chamber right there. There you have a cup with some, this much of water maybe, some ml water. And how do you generate the particle? You have a tablet of sodium chloride. You drop it and you turn it on, it's under temperature, so it will give the sodium chloride vapor, so to say. That's how it is. It is pretty standard. I have not seen people are, last time I used the same particle, so I have not seen, maybe these questions I will go back and ask my partner, then why do you guys use the sodium chloride all the time? Because one of them, of course, it is standard, every paper I read that, but it's a good question, maybe something we can use. But another thing is that you understand, even though our lab is biohazardous lab written there, you have to generate some particle which is not hazardous to the others. If I use some kind of a ammonia or something like that, then it may be hazardous to the other guys. You see the point what I'm saying? So sodium chloride is pretty benign. I believe that prompts it to be the standard particle. That's my guess. Again, I will ask him.
Okay, thank you.
Do we have another question from audiences? Okay. If not, maybe we can just give a final round of applause to Professor Mitra for his talk.
Thank you. Thank you very much.
And we sincerely thank you for sharing your knowledge with us.
Thank you very much.